Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the estimation of population parameters, which is a very important problem in medicine, biology, sociology, and other domains. Population parameters are quantities that describe large populations of interest. For example, the average height of the people in Spain, or the average weight of the rats in New York City. Computing these parameters can be very challenging because we typically cannot measure each individual in the population, as this would be too costly or just impossible. Instead, we have to estimate the parameters from a subset of individuals in the population. It turns out that randomly selecting this subset of individuals can be extremely effective. What is fascinating about this topic is that in order to understand why and analyze the estimation of population parameters from random samples, we have to introduce some fundamental results in probability theory. For example, the law of large numbers guarantees that as we gather more and more data, our estimate of the population parameter is eventually going to converge to the true population parameter. Similarly, if we want to quantify our uncertainty about the population parameter, we can use the central limit theorem to build confidence intervals. In this video, we're going to give an overview of all of these ideas, all of the topics related to the estimation of population parameters from random samples, but we're not going to go into detail into each of them because then this video would take 3 hours, and I'm going to try to keep it to 20 minutes. However, you have all those details in the specific videos dedicated to each topic. Let's get to it. We're going to talk about the estimation of population parameters, and let's start by giving an overview of these topics, which again are treated more in detail in different videos. So first we'll talk about random sampling, then we will discuss the bias and the standard error of an estimator. After that, we will introduce these fundamental results in probability theory, which are the law of large numbers and the central limit theorem. And in the end, we'll look at how we can quantify uncertainty about estimates of population parameters using confidence intervals and the bootstrap. Let's get to it. Our goal is to estimate population parameters. Let's take a look at a specific example in a control scenario where we do have access to the whole population, and therefore we can see how good our estimates are. We're going to be working with a population of 4,000 individuals, and specifically the height of those individuals. Our ultimate goal is to estimate the population mean, which is a constant. Okay, it's important to understand that this is a number, and we're going to model it as a constant. We're in a frequentist framework, and our ultimate goal is to estimate this number. The problem is that we cannot measure everyone, so what do? We pick a random subset of people and try to estimate the population mean from that subset. This is a visualization of this data set. This is the whole population, the histogram of heights in the whole population, which we do not get to see. Instead, we pick 400 people out of the population, and we estimate the population mean from those 100 people by averaging their heights. Here we see that the estimate is actually pretty good. What is important to understand is that if we repeat the measurement process, we're going to get a different estimate. If we repeat it again, we get a different estimate. Here, I'm showing you the result of repeating this procedure 10,000 times and plotting the histogram of the sample means, so of these 10,000 sample means. We see that in general, all of these sample means concentrate close to the population mean, so that's good news, but there is some uncertainty. We're going to try to characterize the probabilistic behavior of this estimator of the population mean. In order to do that, we have to define random sampling a little bit more formally. So imagine that you have this population with this big N numbers. Big N is the number of individuals in the whole large population. And you want to randomly sample from the population. So what do? Basically, you pick a number between 1 and big N, uniformly at random, so with probability 1 over n. And then this is going to give you some random indices that you can use to choose from these guys. So each of our random samples, x1 to x little n, these are then our number of data, is going to be one of these guys chosen according to these random indices. Okay, so more intuitively perhaps, we just grab a bunch like little n individuals at random from the population, because we're sampling one by one, realize that we could sample someone twice as each of the samples is taken independently. I haven't said that yet, but this is going to be our assumption. So potentially you could take an individual twice, but that's not going to make a big difference. So now, once we have this little n random samples selected uniformly and independently at random from the population, we can approximate the population mean by just averaging them. Because each of these guys is a random variable, because we are selecting them randomly, the average is also going to be a random variable, which captures this phenomenon that we saw a moment ago, which is that the sample mean computed from the random samples has uncertainty. We're taking a frequentist perspective, as I mentioned a moment ago, where the parameter of interest is deterministic. Okay, this is in contrast to a Bayesian perspective, where we might want to endow the parameter of interest with a distribution. We want to estimate, where we want to characterize the probabilistic behavior of the estimator with respect to this deterministic parameter, which is what we want to estimate. A first question would be, this distribution of the estimator, is it centered at the parameter? Okay, like if we look at the distribution, is it centered at the parameter of interest? This is captured by the bias. If you have some random measurements and a parameter of interest gamma, which in our case is the population mean, the bias of an estimator H computed from this data is just the mean of the error. So you take your estimator minus the true parameter, you take the average of that, that is the bias of an estimator. If the bias is 0, we say that the estimator is unbiased. It turns out that the sample mean is unbiased. This is very easy to prove by linearity of expectation. So we are guaranteed, when we're using a sample mean to estimate the population mean, we're guaranteed to obtain a distribution of sample means which is centered at the true parameter. So, that is kind of good news. But is this enough? Well, not really, right? Because we would still be centered if the distribution of sample means looked something like this. And then, with quite a bit of probability, we would have a pretty bad estimate. We would have quite a bit of error if the distribution was very spread out around the population mean. So an estimator being unbiased is not enough to guarantee that it's going to be accurate. This is why we introduce the standard error, which is the standard deviation of an estimator around its mean. And if that estimator is unbiased, then it corresponds to the mean squared error of the estimator with respect to the true population parameter, because the true population parameter is the mean. Okay, so this just follows from the definition of variance. Intuitively speaking, the standard error tells us how concentrated this distribution is around the population parameter for an unbiased estimator. We proved this result in our video on standard errors, where we showed that the standard error of the sample mean is equal to the population standard deviation, how spread out the original population is, divided by square root of n. This is a very important result because it tells us that this distribution is more and more concentrated as we gather more data. This follows from the fact that the variance of a sum of random variables is equal to the sum of the variances. Importantly, there is no dependence on the size of the original population. All that matters is the number of samples that we're obtaining the number of random samples that we're using to compute the sample mean. So let's take a look at how the distribution looks for our height data. For n equals 20, we have this distribution, and now as we increase n, what do we expect? We expect this guy to be less and less spread out by this result that the standard error decreases with square root of n. And that's exactly what we see. This is for n equals 100, and this is for n equals 1000. We can now plot a lot of sample means for different n's with respect to the population mean, which is this line here. And what we see is that indeed the spread for each n decreases with square root of n, in particular with the population standard deviation divided by square root of n. This implies in particular that if we look at the mean squared error between the sample mean and the true population mean, which is there, it goes to 0 as n goes to infinity. But, maybe we're not necessarily interested in the mean square error, but rather in the deviation between our estimate and the population parameter. So we might say, okay, we want to have a deviation of less than, let's say, 1 centimeter in the case of the height with very high probability. Is this guaranteed by this result that the mean squared error goes to 0? One feels that it should be, but it's not immediately clear. So what we're really asking here is if this sequence of probabilities, which gives us the probability of a certain deviation from the population parameter, is that also going to converge to 0? Yes, exactly. It is to 0, right? Because we want this probability to be very small, just to be clear. We want the probability of a deviation from the true population parameter to be very small. Do these guys go to 0 when the MSE goes to 0? This is kind of a fundamental question. And this question can be answered using Chebyshevs inequality, which tells us that a random variable with small variance cannot be far from its mean with high probability. This actually implies that the sample mean will actually converge to the population mean with high probability. We actually prove a result that is more general than that using Chebyshevs inequality. We prove that if we have a sequence of independent random variables with a certain mean and finite variance, then their average or sample mean is going to converge to the population mean, not the population mean, sorry, to the mean of each of them. We're assuming that each of them have the same mean with high probability, in the sense that if we look at a deviation by any epsilon, eventually if we make n large enough, the probability that the sample mean deviates from the mean by epsilon is going to go to 0 with n. This is given by Chebyshevs inequality. Okay, it converges to 0 for any epsilon. This is a more general result. When we apply it to the population mean, it gives us consistency of the population mean. Consistency just means that if we estimate a parameter from n random measurements, okay, a deterministic parameter of interest gamma, when we take n to infinity, the difference between the estimate and the population parameter, the probability that that difference is greater than any epsilon, no matter how epsilon is, eventually goes to 0. Okay? If that happens, then we say that an estimator is consistent. And it turns out that the sample mean is consistent. So here we see sample means for different n's, and we see that this is basically a deviation of epsilon. In this case, epsilon, I think, is something like 0.5 centimeters, or maybe even a bit, 0.25 centimeters, I think it is. Eventually, as we make n larger and larger, the sample means are going to be confined with probability 1 to be within epsilon of the population mean. Okay, this is what we mean by saying that the sample mean is a consistent estimator. And this is given by the law of large numbers, and we also see it numerically here for our height dataset. So we have now a bound on the deviation between the sample mean and the population mean. So we could ask ourselves, is this a good, this is the Chebyshev bound that is used to establish the law of large numbers. We could ask, does this give a good approximation of the probabilistic behavior of the sample mean? And it turns out that it doesn't. Okay, so here, these are Monte Carlo estimates of the probability of deviating, obtained by just randomly sampling from my data and looking at the deviations. And what we see is that the bound is actually, it is an upper bound, so that's good news, because this is what we prove in the video on Chebyshev bounds and the law of large numbers, but it's actually a really bad approximation. So in general, the law of large numbers tells us that there's going to be convergence, but it doesn't characterize the distribution of the sample mean. In order to characterize the distribution of the sample mean, we need a more powerful result. By more powerful, I mean a result that actually gives us information about the distribution, not only about the convergence of the estimator. In order to understand the distribution of the sample mean, we have to understand the distributions of sums of independent random variables. So here, if we look at discrete random variables, if we consider the sum of two discrete random variables, the PMF of the sum is given by the convolution of the PMFs of the individual random variables as long as they are independent. This convolution can be seen as a moving average of one of the PMFs. By moving average, I mean we fix one of the PMFs and then we move the other one on top, okay? I know that I'm going a little bit quickly here, but again, this is just an overview. You can look at the video on sums of random variables in order to get more information. But I want to kind of emphasize the high-level points. Here, the high-level point is that if we want to understand the sample mean, we have to understand sums of independent random variables. And for discrete random variables, the PMF of the sum is given by the convolution of the PMFs. If we have n random variables, then the PMF of their sum is going to be the convolution of the individual PMFs. Let's see what happens when this convolution occurs over and over and over. I mentioned that it's kind of like a moving average because this operation actually smooths out the PMF. And if we look at it, you know, this is 1, 2, 3, 4, 5, 6. When n is even not that large, the iterated convolutions smooth the PMF into something that is quite Gaussian looking. In fact, if we put a Gaussian on top of these PMFs, we see that at the beginning, obviously, the approximation is not great, but eventually the approximation is actually pretty good. In this example, by the way, each individual PMF corresponded to the number of points gained by a soccer team in a game, and then we look at how many points they gain over several games. The details are in that specific video. Okay, so we saw what happened for discrete random variables. Now we often would like to also compute averages of continuous quantities. So let's take a look at the sum of independent continuous random variables. Well, we see a very similar result where the PDF of the sum is equal to the convolution of the individual PDFs as long as these continuous random variables are independent. And a convolution is just fixing one of the PDFs and then having a moving average by putting the other PDF on top and integrating. Again, more details in that specific video. When we have n PDFs, if we look at the sum is going to be the convolution of all the PDFs. Up to now, we have only talked about sums, but what we're actually interested in is in averages, in sample means where we're dividing by the number of random variables that we're summing. It's easy to establish that if the sum is a convolution, then the average is also going to be a convolution that is going to be scaled because we are dividing by n. So let's take a look at some averages of random variables that have a uniform distribution between 0 and 1. In this example, each of them was supposed to be the supply of coffee provided by an importer, and all of these importers are independent. When we look at this average of uniform random variables, what we see is that quite rapidly, the iterated convolutions make the distribution look quite Gaussian. And if again we superpose a Gaussian with that mean and that variance, we see that the Gaussian approximation becomes very good very quickly. So the central limit theorem guarantees that this is going to happen if you have a sequence of random samples and you take the first n entries in the sequence, that is going to be approximately, and you take, the average or the sample mean of the first n entries in the sequence, that sample mean is going to be approximately Gaussian with a mean and standard deviation, which in the case of the estimation of the population means correspond to the population mean and to the standard error that we had mentioned before. Okay, so here I'm actually showing you the central limit theorem for the specific case of estimation of population mean. In that case, the sample mean converges in distribution to a Gaussian, which has mean equal to the population mean and standard deviation equal to the standard error. Let's see how the central limit theorem, well, let's take a look at the approximation that the central limit theorem suggests in the case of the height data. So we are at n equals 20. The central limit theorem tells us that as n goes to infinity, we're eventually going to be Gaussian with mean, mu, pop, and standard deviation equal to the standard error. But we can take a look at what that approximation looks like also for finite n. And that's what we do in statistics. Even though the central limit theorem only gives us guarantees asymptotically, we actually apply this approximation in a bit of a cavalier way to finite n. So here what we're going to do is we're going to standardize the sample means that we obtain by taking 20 samples from our population of heights, by subtracting the population mean and dividing by the standard error. And what we see is that this is almost like a, almost exactly a Gaussian, even though n is just equal to 20. For n equals to 100 and n equals to 1000, we only get a better approximation. Okay. So remember that we have motivated introducing the central limit theorem because this Chebyshev bound that we used to prove the law of large numbers did not give us a good approximation of the deviation between the sample mean and the population mean. So we can see whether the central limit theorem or this Gaussian approximation inspired by the central limit theorem gives us a better approximation. And the approximation is amazing. So indeed it does. But now the question is, how can we exploit this to quantify uncertainty about our estimator of interest? And the way we can do this is by building confidence intervals, where the idea is to report a range of values that contain the parameter of interest, in our case the population mean, with high probability, for example 95%. Just to explain this in a bit more of a visual way, by this Gaussian approximation provided by the central limit theorem, we know that if we sample a sample mean, it's going to be close to the population mean, and its distribution is governed, is basically a Gaussian that is centered at the population mean and has a standard deviation that is the standard error, which is the population standard deviation divided by square root of n. Okay, we know that. So we can easily come up with an interval that contains the sample mean with probability 0.95. But now, of course, when we actually take n samples from the population, all we get to see is the sample mean. We don't know the population mean. But if we can estimate this width, we can actually put an interval here of the same width. And now, because this guy is within that interval with high probability, for example, 0.95, then this guy, the population mean, is going to be inside this interval with probability 0.95. And this is exactly how we build confidence intervals. Of course, we have to assume that that the sample mean has a Gaussian distribution, and also that we know this width, which requires knowing the standard error, but we will get to that in a moment. Okay, but imagine that you can actually estimate that width, then you can build confidence intervals around each of your sample mean estimates. So here I'm showing you the confidence intervals associated to different sample means observed from n measurements, and this is the population parameter. So you see that the population parameter is within the intervals except for this guy. That's what we mean when we say with probability 0.95, 95% of the time, the intervals actually contain the population mean. So we derive this in a separate video, but basically you can show that a confidence interval for the population mean is an appropriate constant that depends on the probability that you want for your confidence interval times the standard error, and then you take that and you do the sample mean minus plus that. That's what we meant by this width. That constant for the case of 0.95 is just 1.96. This requires knowing the population standard deviation, which of course we don't know. And here what we do is we estimate it from the actual data by using the sample standard deviation. So now let's take a look at some intervals obtained from the height data for n equals 20. Realize that when we try to quantify uncertainty, we only quantify it from these 20 samples. We cannot, sample the sample mean over and over and over, which would be ideal. We have to quantify the uncertainty just from the available data. That's why confidence intervals are challenging to build. Okay, these are confidence intervals built from just 20 measurements. Notice that the widths are actually quite different, and this is due to the fact that the estimate of the population standard deviation from these just 20 samples, which we need to establish the width of to determine the width of the confidence interval, that estimate is not that accurate from just 20 samples. So this is why we see this difference in widths. But nevertheless, we do get confidence intervals that contain the population mean with high probability. If we increase n to be equal to 100, the confidence intervals shrink, because now, because in our formula, we have this dependence with square root of n, which is quite satisfying, right? Because this means that as n increases, we're going to have less and less uncertainty around our estimate. So this is why when we look at confidence intervals for n equals 20 and n equals 100, boom, the confidence intervals have shrunk because the standard error of the sample mean for n equals 100 is smaller. Notice, however, that the probability that the confidence intervals contain the true parameter, which is this line here, stays the same because we're still fixing them to be 0.95 confidence intervals. All right, so we have built these confidence intervals for the population mean, but what if we don't know this formula? Because realize that here we're relying on two things. We're relying on the sample mean having a Gaussian distribution, and we're relying on the fact that we know the standard deviation of that Gaussian distribution, because essentially by the central limit, not by the central limit theorem, but by the fact that we have a sample mean and the standard error decreases with 1 over square root of n times the standard deviation, the population standard deviation, we know how to compute this standard error. Okay, I said that in a very convoluted way, but basically we have a formula that comes from an analysis of the sample mean. But what if you don't have that formula for another estimator? For example, we want to put confidence intervals on a correlation coefficient, which we're going to do in a moment. Well, in that case, you would want to estimate your standard errors computationally. How can we do that? Well, we can do that by applying a pretty strange idea, which is sampling from our available measurements as if they were the population. This is called the bootstrap. So in the bootstrap, we take our available measurements, which are these small n measurements. Realize it's just the small n measurements, not measurements from the whole population. And we sample from those independently and uniformly with replacement in the same way that we did for the general population when we were taking random samples. So here we're going to build many batches of little n samples by sampling from our data uniformly and independently at random. Okay, we call these samples bootstrap samples. What do we do with those bootstrap samples? We compute the standard deviation of the estimator computed from the bootstrap samples. To make this very clear, we basically have our data, which is this histogram here in gray, which is going to be fixed, and then we sample n bootstrap samples. I think here this is probably from 400 measurements, so we sample 400 measurements at random from the 400 original data points, and we compute a sample mean. And then we repeat that with 400 other bootstrap samples. Realize that the original data remains fixed because those are the data that we have. And we compute the sample mean of those 400 new bootstrap samples. And we repeat this over and over and over and over, and then we compute the standard deviation of all of these sample means. And it turns out that that is a very good estimate of the standard deviation of the standard error of our original of our sample mean. So here we have the true density of the sample means that would be obtained by taking 400 samples from the population over and over and over. And here is the distribution of the bootstrap samples that are obtained just from a single data set of 400 measurements. And the two distributions are actually quite similar. Of course, they're not centered at the same place. Why? Because this guy is centered at the population mean, and this guy is centered at the population mean, but the population mean of the data, which is just the sample mean of the data. So there is this shift. But the standard deviation is actually quite close. This bootstrap standard error is a pretty good estimate of the true standard error of the sample mean for that n, and it doesn't require knowing this formula that it scales with the population standard deviation divided by square root of n. So this means that you can just plug it into a confidence interval and obtain a confidence interval for your estimator of interest, in this case, the sample mean. So we can apply this to try to build confidence intervals for a quantity where we don't have a formula for its standard error. So here we have a bunch of data points, which are the foot lengths and the associated heights of a group of people. Want to estimate the population correlation coefficient, which is the correlation coefficient over the whole population. But we only have 100 samples. So we can compute the sample correlation coefficient from those 100 random samples. I hope I said 100. I don't know if I said 100 or 400, but anyways. So we can compute the sample correlation coefficient from those samples. We get a certain estimate of the correlation coefficient. Now we would like to put confidence intervals on it to know how uncertain we are about this. So how do we do that? Well, we build bootstrap Gaussian confidence intervals. We take these 100 samples and we produce batches of 100 bootstrap samples over and over and over and over, and then we compute the correlation coefficient associated to each batch, and then we compute the standard deviation of those correlation coefficient, and that enables us to build confidence intervals under the assumption that the estimator is Gaussian and that the bootstrap standard error is a good estimate of the standard error. And in this case, this actually works out pretty nicely. And we get like a good coverage. So 93.7% of these confidence intervals actually contain the true correlation coefficient, which is here. In this case, we can do this because we have the ground truth population. We can actually check. If I try to apply this to just 25 samples, then it doesn't work so well. Okay, so here the sample correlation coefficient is this. I want to put a confidence interval around it. And the problem is that actually I'll show you in a moment that it doesn't work so well. I thought I had this graph that shows that this doesn't work as well for 25 measurements. You will believe me for now. We will see it in a moment. The reason this doesn't work so well is because the distribution of correlation coefficients is actually not Gaussian. Again, we can compute this distribution in this case because I can basically take 25 samples from my ground truth population over and over and over and check how these correlation coefficients look like, which I wouldn't be able to do in practice because in practice I would only have 25 samples. But here we can verify that the distribution is actually not really Gaussian. In the case of the 100 measurements, in case you're wondering, it is much more Gaussian. So that's why our approach worked out in that case. In cases where things are not Gaussian, we can apply a different construction of confidence intervals based on the bootstrap, which builds on this intuition that the bootstrap distribution that we obtain from our fixed data is a shifted version of the true distribution. Meaning that if this guy is centered at the population mean, in this case, like let's reason about the population mean and then we will talk about applying it to other population parameters, then if we take basically what we would want is an interval around the sample mean that contains the population mean with high probability, because this distribution is basically the same distribution but shifted approximately, then we can just take an interval that contains 95% of this distribution, and that's going to contain the population mean with high probability if it is true that the bootstrap distribution is just a shift of the distribution of the original estimator. You can actually prove that this is still going to work out even if the distributions are not Gaussian, but they become Gaussian if we transform them with a monotonic transformation. Okay, I'm not going to get into the details, but there's a separate video on that. So here I'm just showing you that the two standard deviations are similar. So it is true that one distribution is a shift of the other, and that motivates constructing confidence intervals by taking, so these are our samples, these are estimator, taking many bootstrap samples and computing the percentiles of the bootstrap samples that give us an interval that contain these bootstrap, okay, not the bootstrap samples, the bootstrap estimator. So we need to compute the estimator from the bootstrap samples over and over and over. If we build an interval that contains these estimates obtained from the bootstrap samples with probability 0.95, then that is going to be a confidence interval for the original parameter under some assumptions. And these assumptions are, they are both Gaussian or they can both be transformed into Gaussians. The first assumption holds for the sample mean and the population mean. The second assumption actually holds for the correlation coefficient. Again, there are more details in the corresponding video. Okay, and then we build the confidence interval in this way. So this shows you, this is what I was referring to before. This is for n equals 25. This is the true correlation coefficient, and what we see is that the Gaussian the Gaussian confidence intervals, which are in gray, fail to contain the population parameter more often than the percentile confidence intervals, which are able to adapt to this skewedness, here you see it quite clearly, of the sample correlation coefficient estimator. Okay? And in fact, we get better results with the percentile confidence intervals. They contain the true correlation coefficient more often than the Gaussian confidence intervals when n equals 25, and they're a little bit shorter, because of course you can always contain the population parameter with high probability if you use extremely large confidence intervals, but those are not very useful because they don't quantify uncertainty as well. All right, so what have we learned? We have learned about random sampling. We have discussed the bias, which is the error on average of an estimate obtained from random samples. The standard error, which is the spread of the distribution of an estimator around the true parameter when the estimator is unbiased. We have talked about the law of large numbers and how it tells us that as we gather more data, eventually we converge to our population parameter of interest. We have talked about the central limit theorem that characterizes the distribution of the estimator asymptotically and also inspires a Gaussian approximation, a Gaussian non-asymptotic approximation that we can use to build confidence intervals. That approximation requires knowing the standard error of the Gaussian, which can be estimated computationally using the bootstrap, and the bootstrap can also be used to build confidence intervals directly, which can be applied to other estimators that are not Gaussian but can be transformed into Gaussian by a monotonic transformation. And that's it. That's all I have. Thank you very much.